Dans les 3 prochaines
In the
séquences,
next 3 videos, we will take interest in stellar formation and evolution. In this first video, we will see under which conditions a cloud of gas and dust can start its collapse until eventually forming a star. As we see here, stars form in groups, from a gas cloud which fragments due to local inhomogeneities, and the resulting pieces if they are over a certain mass, or over a critical radius, known respectively as Jean's mass and Jean's length. These pieces contract and warm up to the point where nuclear reactions of hydrogen fusion starts and gives birth to a star. As we said, stars are from fragments of a nebula. We draw here a nebula fragment. This fragment, if it is over a specific mass or a specific radius, will collapse and as such become smaller and smaller and denser. We will see that it implies that the fragment will warm up. Let us consider a nebula with a given radius r, and as usual, a given density, a total mass and a total number of particles, composing the nebula, atoms and molecules. The nebula fragment is isolated, and we can then use the viral theorem, which tells that, averaged in time, the kinetic energy is minus 1/2 of the potential energy. We can express the kinetic energy as a function of temperature, 1 divided by 2k T by degree of freedom. A three-dimensional space means 3 degrees of freedom, and n particles leads to n degrees of freedom, times k the Boltzmann constant, and T the temperature. If we now assume our nebula fragment to be more or less spherical in shape, we can compute the potential energy like we did in the previous video, 3gm squared, m being the total mass, over the radius of the nebula. If it can be approximated to a spherical in shape, both quantities are equal by the viral theorem. And we have then gm squared divided by r equals 3nkt. As we have seen with the viral theorem, and in particular with the simulation shown in the video 1.4 on the viral theorem, if there is a lack of kinetic energy relative to the potential energy, the gas cloud in this case will start to collapse. Let us take the aforementioned equation. We have 3nkt less than 3 divided by 5 gm squared divided by r. By rearranging the terms, we have kt smaller than gm averaged that we introduced in previous videos over r times m. With m averaged being the mean mass, m over the number of particles. If we now also assume that m equals 4 divided by 3 pi r to the third power times the density, supposing that the density does not depend on the radius, and that it is therefore constant everywhere in the cloud, we can then rewrite this inequality in another form. R goes from the denominator to the numerator, since we invert the inequality. R greater than square root of 15 kt divided by 4 pi gm sigma. The mean mass can be expressed as a function of the mean molecular mass we previously talked about, times the atomic mass unit. If there is a lack of kinetic energy to support the shape of the cloud, then it will collapse. And the inequality we wrote here comes to defining a critical radius, which is the minimum radius a cloud of a constant density can have before collapsing. The radius we just defined is called Jean's length, named for the astronomer who first introduced it. It is the square root of 15 kt divided by 4 pi gmp. This length is the minimal radius from which the gas cloud collapses at a constant density. If r is bigger than Jean's length, then we have a collapse. A star can potentially form from such a collapse. There is some mass contained within Jean's length, which allows us to define Jean's mass. The mass inside Jean's length. It is the limit mass before the collapse of a cloud of a given radius, Jean's length. We have a collapsing cloud, and we now seek to know the time taken for the cloud to collapse. This is called the freefall time. How much time does it take for each point of a roughly spherical cloud to collapse into a single point, say at the center of the cloud? We have a cloud with a radius r, just like previously, and we have a particle leaving from the edge of the cloud and going to the center of the cloud. We can consider a straight line to actually be an ellipse of infinite eccentricity. I draw here another ellipse with a smaller eccentricity, and again another one with another eccentricity. You recall Kepler's laws. We already see the drawing here, which said that the orbital period is dependent from the eccentricity. All trajectories I am drawing here. If, for example, a particle leaves this point and follows this path until reaching the center, it will take the same time as if it took this other path here. We thus consider that we have a particle here, or an extremely eccentric orbit, with a radius of r divided by 2. The freefall time is therefore the time taken to go from this point to the center, which corresponds to half the orbital period. The orbit has a radius r divided by 2. The freefall time is p, the period of the orbits drawn here, minus p being independent of the eccentricity, which is what we're going to compute with Kepler's third law, divided by 2. This period, according to Kepler's law, is 4 pi divided by gm squared. And here is the 8 to the third power, which is the cube of the semi-major axis. The orbital semi-major axis is r divided by 2. We put the total mass of the cloud in a point here at the center of the cloud. If we rewrite the equation, we get this. It is the period of the relevant orbit. The freefall time is equal to the period divided by 2. Since the period is squared, I have a square root here. The freefall time is 3 pi divided by 32 gp. What we especially notice is that the freefall time only depends on the density p. Here are a few examples of freefall times, a few orders of magnitude. We have here the density of some objects, including the universe as a whole, the density of which being 10 minus 27 kg divided by m to the third power, and we have the corresponding freefall times. We see that if the whole universe collapsed without any resistance, it would take 10 and 11 years. This is, of course, an order of magnitude. A galaxy with a density of roughly 10 minus 21 kg divided by m to the third power would collapse in roughly 100 million years. Clouds in the interstellar medium take tens of thousands of years to a few million years to collapse. The solar system would take 1,000 years, and a star such as the Sun, with a density of roughly 1.4 tons divided by m to the third power, would collapse in half an hour. Yet the Sun does not collapse in half an hour. To understand this fact, let us have a look at the energy balance of the Sun. If we look at the total energy, Its change is equal to the change of potential energy plus the change of kinetic energy. This is equal to the energy loss rate, namely the sun's luminosity times a time unit. For an isolated system, we have the viral theorem, which tells that du plus 2 dk equals 0. We now have a system of two equations with two unknowns, which is easy to solve. We get that du equals minus 2L dt and dk equals plus L dt. This means that the star radiating implies a loss of potential energy. The luminosity of the star creates a loss of potential energy. We also notice that half of the lost potential energy is gained, converted into kinetic energy. If there is a gain of kinetic energy, it means that the star warms up. If there is a warm-up, there is a photon emission by black body or ionization. And if there is photon emission, there is a radiative pressure exerted by the photons on the external layers of the collapsing stars. This radiative pressure counteracts the gravitation and prevents the star from collapsing in a time of the order of the freefall time. We can go some steps further and estimate the lifetime of a star by saying that this lifetime is the time needed to shine half the potential energy. Since this is what the star loses, we have then half the potential energy, U divided by 2, radiated at a rate corresponding to the luminosity of the star. In the case of a sphere, it is simple. 3 divided by 5 divided by 2, or 3 divided by 10, times gm squared, the mass of the star, over r. This is, so far, the potential energy of a sphere, divided by 2. And the L we have here. This is called the Kelvin-Helmholtz timescale. It is the lifetime of a star if it radiated half of the available potential energy. This is, of course, only an order of magnitude. If we make a numerical application from one solar mass, we find that the Kelvin-Helmholtz timescale is around 10 million years. The Sun is 5 billion years old, so the timescale is roughly 500 times too small. In the case of the Sun, a star of one solar mass, there is therefore another energy source that makes the stars shine. We have seen in a simplified manner how the stars form and how they take their energy from the gravitational collapse on the one hand and the nuclear reactions on the other hand. As you have indeed understood, death and birth of stars are deeply linked. Generations of stars follow one after the other. Young stars are formed from the material, the remains of dead stars. It is within diffuse nebulae, like the one pictured, that stellar remains and rising stars live side by side. In the upcoming videos, and in particular in the very next one, we will see how stars evolve. Once they started up the nuclear reactions in their center, we will see what are the observational methods to study the many steps of their life.